for sharing the slide. So I'm doing in this project on the computational simulation of the Undoped and P and N-type doped the Cis-polyacetylene using density of state and absorption spectrum. Next slide. Okay. So the objective of this project. Second, just second. So the objective of this project is actually to understand the charge transfer because here we use two type dopants, and we want to see what happened when we use this one, and those dopamine actually control the conductivity. So we are checking those things, and we also prove that the doping and we inject the charge, they actually give the result, and those results are more or less same. Next. So here we want to explain that the conductivity, electrical conductivity. So electrical conductivity actually the property of the material which determines how well the conductivity, it shows the conductivity. So in the first, the right side, and we are able to see the general form of the material, that how it looks if the band gap between the conduction band and valence band is more, it's that material behaves like an insulator, and if less than the insulator, then it behaves like a semiconductor, and if the conduction band and valence band, they are overlap with each other, it's behave like a metal. And in the right side there is another figure. So it's actually shows our project, that how it goes on. And there in the first, that one in a neutral state, it shows that in a semiconductor state, in this valence band is occupied, and the conduction band is unoccupied, and this one is in a semiconductor phase, because there is band gap. We are able to see the band gap. When we remove some electron from the conduction band, then we are able to see that the LUMO is near to the valence band, and so they are overlap with each other. So it now behaves like a conductive material. Then if we add some electron inside the polymer or polyacetylene, here we use polyacetylene, then the their HOMO is go up, and it's overlap with the LUMO, so its behavior, it's like shows the conductivity of the material. Next slide. Okay, so for this project, we actually use three model of the polyacetylene, cis-polyacetylene we used, and first one is the undoped material, undoped one, and there we then inject any dopant. In the B, figure B, one B, in there we inject P type dopant, and P type dopant actually is like they accept the electron, and p-type and in figure A 1C, here we used added two type dopamine, P and N. So P actually p-type dopamine is an acceptor element, and N-type is a donor element. So there in the p-type and dopamine, there there is a sodium, it's a blue, there is a sodium ion. So it's easily can share the electron to the fluorine, and fluorine and we are able to see this one that fluorine can easily take that electron from the sodium. So why we use this type of dopant? That because we want to prove that using dopant the conductivity of the material will be increased. Next slide. Okay, here we did density of state um, graph shows density of the state graph for the undoped, doped, and the co-doped model. So first, and the neutral first that the first panel A neutral, B cation, and C is anionic state. So from the figure we are able to see that there is a peak that occupied orbital, that one is 0.4, and the unoccupied is peak is 0.8. So there is a band gap. It's visible band gap. But if here from the figure 1b, we are able to see that the occupied and unoccupied they are actually overlap with each other. So it behaves it shows that when we remove electron from the model, it behaves like a conductive material. So same thing happened with the anionic state, but if we see all the figure, only we are able to see that the this figure like 1b, that one actually show more conductivity. I want to show you on the table. Professor, just could you please click that? Yeah, so there we are able to see from this table we are able to get a conclusion that when we did anionic and cationic calculation, and then the undoped model in a cationic state, that one show more conductivity than others. Professor, yeah. Okay, it's okay. So this one actually we are showing the absorption spectrum analysis, and W is the frequency at a zero state. So in here we are able to see that we already proved that band gap in a cationic state is less band gap, means more conductivity, and when we indeed in the absorption spectrum, it also shows that at zero energy it shows more absorption. Next slide. Okay. And so from this one, we are able to get that the cationic state and the undoped cationic state compared to the other model, it shows more absorption at when wavelength is more. It's like reverse to the absorption spectrum. Next slide. Okay. Now this one we are showing the charge density of the undoped model, and here we actually showed two type position, X and Z, and in the X position we are able to see the peak, and that peak actually because of the electron particle of the electron we are able to see from this box, and there that peak means in that stage the that blue cloud shows more charge density, and there in the Z position we are able to see that there is a high peak. that means there is this one shows more charge density, and this the third oligomer and the second oligomer, there is orbital, they actually almost overlap with each other. That's why this stage actually shows the conductivity, proves the conductivity of the result. And similarly, in the homo orbital, we are able to see that at the edge, in the x position, at the edge of the box there, it shows more charge density. Next slide. Similarly, these things happen that high peak means it shows the more charge density, and it's happened in it shows the third oligomer, and in the LUMO plus one it shows more charge density at the edge of the box. And I want to explain the doped one. What's the next slide? Next slide. Okay, so because in this model we used the dopant here. So for the dopant, we are able to see that and where that this doping is added in the oligomer, there is no charge density. We are it's visible from this graph. So we are getting this conclusion that this doping actually affect the charge intensity, and we are able to see that the charge density almost shift on the other oligomer, and in the middle position it shows the more charge density. Next slide.
Okay, let me suggest to wrap up and go to conclusions, because we are
just go to the MD simulation and then conclusion. MD DOS. Okay, so after that we did MD. Professor, could you please show the DOS graph of the MD? Okay, so after that we did heating and MD simulation. Actually, from the MD simulation, we are getting that after doing this one, the band gap decrease a lot. So all of them, it's a neutral state. There is no removing or no adding electron, but it behaves like a conductive material. And then conclusion. Okay, so after that we had a conclusion, and that when we compare our result, undoped material.
Sorry, just a second. Keep talking.
Okay, undoped material actually behave like more conductive material, and we actually adding doping and injecting charge, and those are control the conductivity of the cis-polyacetylene that material. And we are proving that the injecting charge and adding dopant more or less shows the same result. Let's say.
Okay, please join me in thanking Kea.